Sir, am I audible?
हाँ सर आ गए क्या?
Yes, sir.
सर नमस्ते.
हाँ नमस्कार. Bivas, I hope I am audible now.
Yeah, audible sir, very audible.
Okay, great.
Sir, can we start?
Yes, definitely.
Yeah, Sir, please start.
Okay, good afternoon, sir, and good afternoon, everyone. A very warm welcome to all the participants. I, Sejal Pal, third year student, feel truly honored and welcome you all to the session of our faculty development program. It's my immense privilege and pleasure to introduce our esteemed expert, respected Professor Surya Prakash sir. Sir is currently serving as a professor in the Department of Computer Science and Engineering at the IIT Indore. He is highly respected scholar, researcher, and mentor, known for his remarkable contribution to the field of machine learning, deep learning, biometrics, pattern recognition, computer vision, image processing, big data, and digital heritage preservation. Respected sir completed his PhD in computer science and engineering from IIT Kanpur, his MS from IIT Madras, and his BTech from Institute of Engineering and Technology, Kanpur. With an outstanding academic and professional journey spanning over 2 decades, Sir has served in various prestigious positions at IIT Indore and has continuously contributed toward excellence in the research, teaching, and innovation. Sir has an exceptional publication record with numerous research papers published in reputed SCI, Scopus, IEEE, Springer, Elsevier, and ACM Index journals and conferences. His research work in areas such as biometric security, fingerprint authentication, medical image segmentation, computer vision, and 3D air recognition has received wide international recognition. Sir has also received several prestigious recognition and currently serves as an associate editor and editorial board member for reputed international journals. He is also a senior member of IEEE and actively contributes to the global research community through reviews, editorial responsibilities, and internal collaborations. Now, I would like to invite Sir and take over the session. Sir, can we start the session? Sir, can we start the session?
Yeah, please. I think sir is muted.
Sir, your mic is off. Can you please turn off on the mic?
Wait for a minute. I think that he is trying to reconnect or whatever the problem is.
Sir, is there any issue regarding video or audio? Because of some issue, we will start the session after 10 minutes at 2:45 p.m.
Yeah, really sorry. Actually, I mean, there was some issue in my
Sir, no issue, sir.
camera. Yeah, so we can start now. I'll just share my slides and then. Yeah, Bevas, I think my slides must be
Yeah,
visible.
sir, visible, sir.
Okay, okay. Yeah, I just take 1 minute and then I'll start.
Yeah, sure, sure.
Yeah, good afternoon, everyone. In today's session, we are going to discuss large language models, which are also known as LLMs. So let's first understand what do we mean by language model, and then we'll extend that to large language model. So when we are saying language model, the model refers to those models which are used for generating the text. Okay? Language models in general are the models which are used to generate the text. So when we are doing this task of generating the text, what exactly we do? So we can say in a very simple term that when we are generating the text, at any given time instance, we are trying to find out in our sentence what is going to be the next word, right, or next token. In the context of language models or LLM, we call that next word as next token. So the task of any language model is to predict the next token or find out what next token is going to fit in a sentence which, let's say, you are trying to make or trying to complete. So let's understand that with the help of one example. So let's say we have a sequence of words or tokens like machine learning edge, right? I mean, somehow we have, let's say, got these three words, and then we are trying to find out what is going to be the most suitable word after this. So there are multiple options. For example, powerful, important, used. Right? There are many options are there which can be used for for completing this sentence. So, but which one is going to be the most suitable, and that we are going to see, or that we are going to find out with the help of language model. So language model is actually going to consider all these words, and then going to tell us what is going to be the most suitable word. So for example, here let's say we say that the powerful is the right word. Okay, so we can say the next word is going to be powerful. So the sentence becomes machine learning is powerful. Okay, now you might be thinking, how do we know whether powerful, or how does the model knows whether it is going to be powerful or important? So this knowledge, these models attain through the training. So before using any model for prediction or for generating the text, the pattern undergoes, the model undergoes through training, and in that training, the model learns the patterns, and then based on that, it is, it is when it is given the responsibility of generating the text, it generates. Okay. So how does it know whether powerful is important, powerful is suitable, or important is suitable, or used is suitable? So this is the model finds out with the help of the training that it has undergone through. So every language model is going to be first trained with the large text data sets, and then from there it gets the training, it learns the patterns and all that, and then based on that it is going to predict. So these details we'll be looking at slowly and slowly. So let's see one more example. We have, let's say, the sentence deep learning models are. This is the sentence given, and then we are trying to find out what is going to be the next word in this. So let's say powerful is going to be the next word, or the widely is going to be the next word, or used is going to be the next word. So again here, we have all words available with us, and then the model is trying to find out which one is going to be the most suitable word. And for that, the model basically computes the probability with respect to every word, or probability with respect to the token. So let's say, like n words are there, and remember, whenever the model is predicting a word, it is actually picking a word from the dictionary. So with respect to every model, we have the concept of dictionary, which consists of all the possible words that model can pick. Okay, so from that dictionary, the model is assigning probability to every word. For example, powerful, widely used, or maybe some many other words. So you can say that it actually assigns probability to each and every word. Let's say you have 10 million words in your dictionary, so it is going to actually assign probability to each of the words there, and then based on the value of the probability, it is going to pick the most suitable. So let's say the model has computed that 0.42 is the probability for powerful, 0.25 is the probability for widely, 0.18 is the probability for use. So then based on the probability, it turns out that powerful has the highest probability. So based on that, it is going to select the word which is having the highest probability, and here we can say the powerful. So any language model is going to compute the probability for all the words that are available in the dictionary, and then depending upon the word which has got the highest probability, it is going to pick that word. Okay. So if you see the history of language models, right now we are talking about large language models, but the language models have existed for long, and we have a long history. You can see. So at the very beginning, so these language models are actually part of the larger area called NLP, right, or natural language processing. So at the very beginning, we had the rule-based NLP. So please keep this in mind that when we are saying language model, it is about having a sentence and then let's say finding out what is going to be the next word in that sentence. Okay, so just keep this in mind. So in the rule-based NLP, we had, it was actually dependent on the manually written rules. For example, if the rule says that whenever the phrase "going to" comes, then the next word is going to be market. Okay, so whenever anywhere the "going to" is coming, then we can predict, or the model predicts that the output is going to be market. Right? It's a very simple example, but you can say the similar thing in similar way, we define the rules, and then based on that, we are doing the prediction. So here, everything is dependent on what rules manually we have written. So, like in this example, if the going to is there, then output is going to be market. Similarly, for other cases also, you can phrase the rule, and then prediction is done based on those rules. Then we had the concept of statistical models, where we I mean extensively n grams were used. So you must have heard of histogram. So in the same way, in case of n gram, we compute the histogram for combination of words. For example, uh, one histogram may be where, let's say, you have a large text given, and in that you count times a particular word is coming. Okay, let's say, see very simple example. I am going to market. Okay, and I mean similar sentences are there. So now you're counting in the whole paragraph how many times the market has come, how many times going has come, how many times grocery has come. So, and you count those words and then make the histogram. That's like simple histogram. Now, in case of n-gram, we are taking the combination of words. For example, we are saying how many times the market has come, right? How many times, that means how many times with the market has come, right? Similarly, we consider other combinations of the words and then find out the histogram for those combinations. So in case of n-gram, in your sentence, going to the is there, and we want to find out what is going to be the next word in the sentence, then this n-gram based model says that which combination has the highest probability, right? So that means along with the, which particular word appears, I mean like mostly, and based on that you choose. So for example, here it turns out that with the market has the I mean, highest count in your histogram, in your n-gram, the market appears to be appearing most often, right? It has, for it the count is very high. So we are picking when we see the in the sentence, we are picking market as the next word. Then we had the RNN, where which stands, I mean, where you have a I mean, the concept of memory, right? So in case of RNN, we are going to read the words one by one in a sequence. Like let's say the sentence is I am going to the. Right? So we are reading these words one by one, and then based on what sequence we have seen, we predict the next word. So when we say the short memory, it means when you are going to predict next word here, you know what has appeared before it, like you know that going to these were the words before that. So based on that, you are predicting that let's say the market is the most suitable word. So in case of short memory, whenever you are going to do the prediction, uh, you look at the words which were previously seen, and then based on that you are finding, based on that context, you are finding out what is going to be the next suitable word. Okay. Then we had the concept of LSTM. I mean, I think these names you must have heard. So here we have, I mean, little improved scenario compared to RNN, and now here we have long-term, I mean, long short-term memory. So you have, like here, these models are capable of not only being able to remember the short memory, but also little long memory. So for example, when you have a sentence like, for buying vegetables, I am going to the. So here, if your model is just having only short-term memory, like let's say it's an RNN, then maybe it will only remember going to the, maybe 3-4 words before the I mean before the word that you are going to predict. But in case of LSTM, these models are able to remember the past of little longer duration. So in this sentence, let's say we are using RNN, and RNN may not be able to remember buying vegetables, right? Without taking into account buying vegetables, it will be predicting, let's say, the next word based on going to the. Okay? But if let's say you have the context, you know that in the sentence buying vegetable has also occurred. So then the prediction will be very good, because you know that for buying the vegetables, you go to market, you don't go to cinema hall, right? Or you don't go to school. So in case of LSTM, these models are able to learn little more context, more past, and then that is why they have better prediction ability. Now, these examples that I'm giving, that I mean, RNN is able to remember only 3 words, or LSTM is going to remember 5, 6, 5 or 10 words. They're just simple examples I'm giving, but in reality, they have much more capability. I'm just citing these numbers to make you understand the concept. Then after that, we had the transformers. So all the language models that we see in current time, they are all based on transformers. So there are some foundational models I've just listed here: GPT, BERT, Llama. They all are based on transformers. And what actually makes these models different from the earlier model is that here we have the we have included, or we have adopted the concept of attention. Right? It's a very, very powerful concept, in which basically we, for any given word, we try to find out what other words are important to it. Right? For example, you are going somewhere, then the model focuses on what are the other words that could be important for going. For example, grocery is coming somewhere, and you are saying going. So then it's possible that for buying the grocery, you are going to the market. So in the case of attention, we'll see this in detail. In case of attention here, for every word, we try to find out what are the other words which are important for it, and then based on that, we prediction, and this gives a very, very powerful way of predicting the text, and for many, many more NLP based tasks. So here you see some examples of transformer-based language models. You can call them large language models. We are just saying they are large because in terms of the capability, in terms of their size, I mean they are large. Right? So I mean, if you want to do some very powerful thing, obviously your models should be large. It will have lots of parameters. So in all these language models, we see that we have a huge number of parameters, like millions of parameters. So, and these models are basic foundational models like GPT, Llama, Palm, BERT. Right? They are different models for different companies, and I think most of them are open source. I mean, like open source in the sense like you can. I mean, they will not be completely open source. That means you will not get the code, but at least you will get the pre-trained model, and then if you want to retrain them, you can do that. There are some models which are completely open where like you can even get the code and also, but these models are not that open. They will only provide you the weights. You can just get them, and then if you want, you can retrain them. Okay. Okay. So in these transformer-based models, we have the notion of three different types of models. For example, some models we say that they are decoder-only models, right? And some which we say that they are encoder-only model, and there are some where we have decoder and encoder both. So in case of decoder-only model, these models are basically focusing on generating next one token at a time, and they look at only at past token. Right? So for example, when you are generating the text using decoder only model, these models are going to read the text from left to right, and then based on that, based on what they have read in the past, they will be generating the next token. Okay? So decoder only models are mostly used for generating the text. In case of encoder only model, these are actually bi-directional. So like here, our movement is only from one direction to the other direction. Like we are just moving from left to right. But you know, when you have to understand the meaning of a sentence, then in that case, you may find that you have to, I mean, you have read something, but to make the things clear, maybe you have to again go back and then read what you have read. So in case of encoder only model, here these models are focusing on understanding the input text, right? They're focusing on understanding the input text by looking at both left and right context. So they are bi-directional. It's not that unidirectional, that you are going to move only from one side to the other side. If required, you can even go back. And for understanding the context and understanding the meaning of the sentence, it is required that you should have the ability to go bidirectional. Okay, so that's why we say that encoder only models understand the text, and decoder only models generate the text. Okay, please remember both these models can. I mean, encoder only models, decoder only models. They both can understand the text, they can both generate the text. But for what purpose they are more efficient, based on that only we are saying that decoder only models only generate text and encoder only models understand text. But they both have the capability. So it's not that they, I mean, with decoder you cannot do the, I mean, you cannot understand the meaning, but only it is, I mean, it is something which differentiates efficiency and design. So you see that here. So in case of decoder only model, like for example, GPT, here, they are trained with the next token prediction, and they are naturally suited for text generation, because here you are only moving in one direction. And in case of models like BERT, which are encoder only models, they are trained with masked language model. Okay, so depending on these trainings, actually the capabilities are getting different. So here, these models learn a strong bidirectional context, and that is why they are good at understanding the task, understanding the meaning of the sentence. They are good at, like, let's say, for example, performing the task like classification, finding of the similarity between the items, and so on. So we need to understand, this is very important to understand the difference, which I just pointed out, that decoder only models can also understand the text. Here we are saying that decoder only models are used for generating the text. These models are used for understanding the text. But it is not the case that, I mean, it's not that decoder only models cannot understand the text. They can also understand the text. Encoder only models can even generate the text, but the difference is in efficiency and design, not in terms of capability. They both are capable, but which model is more efficient for which task? Based on that, we are saying that decoder only model is good for text generation because it's good at that, and encoder only models are good at understanding the text, and that is why we are saying that they are good for this purpose. Okay, so mathematically, when we see any language model, you can, if let's say you look at the task of text generation, language model has different tasks, but here we are just focusing on the task of generating the next token, right, or next word. So let us say you have the tokens in a sequence x1, x2, xn, right? These n tokens you have already there in the sentence. For example, x1 is I, x2 is am, let's say next word is going, and then you are finding out what is going to be the next word in that. So x1, x2, xn, these are the tokens that we have with us, and with the help of them we are trying to generate the new next token. So here you can say I am, let's say you are saying I am going, right? So this is here, this is your x1, this is your x2, this is your x3, and then based on this, let's say you are trying to find out what is x4, right? This you want to find out. So here objective is to knowing n tokens, our objective is to find out what is going to be the next word, that is n plus 1th word we are trying to generate. And so we can say, as I mentioned earlier, that when you are finding out which word is most suitable, which token is most suitable, you're actually trying to find out the probability. So let's say, as I said, you are going to pick the word from the dictionary. Remember, in language model, we have the concept of dictionary. Dictionary contains all the possible words that the model can use. So whenever it comes to find out what is the next token, next word to be used, the model is actually going to the dictionary and then checking the probability for every possible word that is there in the dictionary. So let us say, as I was just mentioning earlier, that given this I am going, you have to find out whether market is the suitable word or school is a suitable word. So you are going to find out with respect to given words whether, when you are choosing xn plus 1 as school, what probability it gets. When you are choosing xn plus 1 as, let's say, market, what probability that word gets. So you are going to basically take all possible words with respect to your dictionary, and then going to compute this what do you say, the probabilities. For example, you are going to compute the probability for xn plus 1, let's say we are saying school, right? So given I am and going, you are finding out what is the probability for this, right? Similarly, you are finding out what is the probability if you choose, let's say, market as the next word uh, in for prediction. So again, market prediction is done based on what we have already seen: I am and going, right? So let's say you get the probability here 0.42, here you get the probability as 0.20. So you know that this probability is higher, so based on that the next word will be predicted. So in general, like whenever you are predicting the word based on what you have seen, you are predicting probability for next possible words, and then whoever gets the higher probability, you pick that. So here we are talking about considering n words and then predicting the next. Now you can extend that for the sentence. So that what is the probability that in your sentence until point, let's say until time t, capital T, you will be generating a sequence of word which is x1, x2, x3, x4, xt, right? What is the probability that you will be getting this sequence? So for that, here we are computing the probability for every word in the sentence, and then we are just multiplying that. So for example, what is the probability that at the very beginning you will get I? Then what is the probability that given I you will get am? Then what is the probability that given I and am you will be getting going? And like that, like that you compute the probability for all the words that you have in your sentence, and then you multiply all these probabilities, and that gives you the probability of having I am going in your sentence. So sequence probability also you can determine by using this way. Okay. So now we are moving to discuss large language models, and then we'll see the details of different steps that these models have. In any large language model, if you see the end-to-end pipeline, like all these steps, the phases through which we go through are these. So we are going to start with the text, right? And then again, assume that your task is to predict the next token. So you are reading a text. That text is being generated, converted to tokens. Then tokens are assigned some IDs. Then we have embedding layer, transformer blocks, hidden state. These are different steps we have when we are processing the text and then trying to find out the next token. So we are going to start with the given text, and then at the end we will be getting what is the next token we expect in that particular sequence of words that we have considered. Okay. So we will see briefly one by one these these steps or these phases which are listed here. Okay. And in case if you have any question, I hope you can unmute yourself and ask questions. So in case you have any doubt, I would appreciate, and that will be actually good also, because otherwise it will be like one directional communication. So if you have any question, I think you can unmute yourself and then ask that, right? So don't hesitate. If you have any question, please feel free to ask. Okay, so let's understand the.
Sir, one question from Ashish Kumar Gupta ji.
What is the question?
Sir, does it check for the next word with highest probability, or there are some other factors or parameters?
Yeah, so finally it is checking the probability only, but to compute the probability, there are factors.
Sorry.
Yes, go ahead.
And the next question is, if word matching process is repeated, how stable is the efficiency of the model, or how it can be mentioned?
Yeah, so we'll see that. So we have just started at the beginning. I request all of you to focus on the part that we are discussing right now. So when you are asking question, you ask the question which is relevant to the part that we have covered so far. And maybe many of your questions will be slowly addressed as we move forward. So just to make the discussion more fruitful, I would recommend you to ask the questions which are related to clarifying what we have discussed so far. Okay.
Okay, sir.
Fine. So I think, yeah. So the previous question, where the probability thing was asked. So final decision is taken based on the probability only. Like as if you remember, we were saying here, we are, let's say, going to pick powerful because it has the highest probability. So final decision is going to be taken based on the probability, but to compute the probability, we're going to see different factors. Okay. So yeah, Sejal, I think you can, if there is any question in the chat, maybe you can read it because I am not able to see the chat. So if there is any question, you can just read that and tell me. All right. Fine. So let's move forward. So the very first phase in our list is the text. So what is a text? So this is the raw input that we are going to, that is going to be provided by the user. Right? You say, in our case, when we are talking about generating the text, it could be, let's say, machine learning is powerful, and let's say you want to find out what is going to be the next. Let's say full stop is going to be the next, or what else can be possible as the next word here. So raw input is, you can say, the input that is provided by the user based on which the text is going to be generated. So in this case, let's say part of the sentence we are saying is the raw input. But in case of, let's say, I mean, as I said, LLM has many applications. For example, another application where you are generating the text is maybe question answer. So you're asking, like nowadays in chat GPT, you put some question and then based on that the answer, you're getting the answer. So in that case, the raw input is going to be your question. So this text is the input that is provided by the user. So in case of sentence completion, let's say it could be, you can say it's kind of part of the sentence. Or in case of question answer, it could be a sentence based on which you are expecting the reply. Okay, so text in a simple sense, you can say it's an input, raw input that is provided by the user. And then on this, different phases of the model are going to work on, and then finally the output is going to be produced. So if you are doing the text completion or text generation, then given n words, the model will be able to predict n plus 1th word. So to do that, to generate the next word, you know that I mean, it cannot be just done in a very simple manner. So it has to, I mean, the model has to understand that clearly, and for understanding the text or the input that is being provided by the user, there are different phases that need to be considered through which the text is going to be processed, and then finally the model will be able to produce the output. So here, you know that our machines are only going to work with numbers. So when we are dealing with the text, ultimately it has to be converted to numbers so that machines can consider that and work on that. So you know, everything is going to be finally using mathematics, right? Some kind of mathematical operations, expressions are going to be used. So that can be only performed on numbers. So here also, if the text is given as input, if you want to perform some operation on that, first it has to be converted into numbers, and then only we can make use of that. So that is why we'll see that in the next step we are going to convert these words or this text word that we are getting here in number, and then based on that we will be performing the further processing. Okay, so before we convert the words into number, what we do, we first the tokens, right? So tokens are little different from the words, because I mean, in simple sense, you can say every word is a token, but in case of token, even our sub word may be also considered a token. So for example, we are saying, let's say, powerful. So in case of token, we may consider power as separate, full as separate. And otherwise, powerful, whenever whenever powerful is appearing in a sentence, we consider that as one word. Okay, but when we are talking about generating the tokens, then in many cases we treat power separately and full separately. So that way the tokens are little different from the words, because in case of token, even sub words may be also, or a sub word may also be considered as a token. Like even in some cases, the characters are also considered a token. Okay, so token means that the small unit which you are going to consider from your sentence and then going to further process word or subword or maybe character. Then we have some standard ways and techniques to perform the tokenization, like this BPE, which stands for byte pair encoding. Uh, it's a standard way of computing the tokens out of the given sentence. So what it does, so whenever you have a sentence like machine learning is powerful, it is going to break it into tokens. And if any there is any space before the word, that is going to be included with that, and along with that space the uh, token is going to be generated. So for example, here machine learning is powerful. Machine is one token. There's no let's say the space bit before that, but before lead learning there is a space. So here the token is learning, and before that we are putting this special character which is actually representing that space. So there is a space between learning, there is a space between is, there is a space between powerful. So these tokens are represented along with the that space, leading space. And this is the way we do in case of BPE tokenization, right? When you are using BPE algorithm for tokenization. So this uh, dot above G is actually representing the leading space before the token. Now, once we get the token, then we are actually going to assign a number to these tokens. Right? That's called token ID. Every token is going to be assigned a unique integer or unique ID. So, for example, machine learning is powerful, so you have broken it into these tokens, right? And you have given them in the form of set. You have these 4 tokens coming out of your sentence, and every sentence, every token in the sentence is going to be given a token ID. Like you can see here, token ID. This one is for machine. This is for learning. This is for is. This is for powerful. Now remember, the token ID will be different for a word when leading, let's say, space is there, and if a space is not there. So for example, for is, if no space is there before it, it will be it will have different token ID. And if the space is there, if space is included along with it, at the like space is present before it, so in that case it is going to be a different token ID. So token ID is going to uniquely identify your token in your dictionary, you can say. So after this, after processing your text, dividing it into tokens and then assigning it to token IDs, now everything is going to be done based on the token IDs. So after this process, after this step, after converting the text into token IDs, now you have numbers. So let's say in your sentence has 4 words, and those 4 words have these token IDs. So now this whole sentence is represented in terms of these token IDs. Okay. Now, if you are just going to consider these numbers, they do not have any meaning by themselves. So what are we going to do next? We are going to represent every word in terms of, let's say, you can say some n features. Okay, every word is going to be represented in terms of n features, and with the help of those feature values you are going to differentiate one word from the other. So okay, and let me give you a very simple example. So let's say you have one word as is. Okay, so is, and let's say every word you are going to represent in terms of a 4-dimensional vector. So for is, let's say you are using feature vector as 1, 2, 0, 1, right? Then there's some, let's say another word machine, like let's say 0, 1, 5, 5. Okay, so this kind of mapping is going to be done for every token or for every token ID that we have in a sentence. And this vector that we are computing here, it is called the embedding for a token, right? So like for is, this four-dimensional vector is the embedding for is. This four-dimensional vector is the embedding for machine, and these vectors are unique to every token. Okay? So for example, if is has this vector, then you will find that no other vector, no other token ID, and no other token will have this vector. So these tokens are, so these embeddings are different for different tokens. So in the process of embedding step, when we are processing our token IDs through the embedding layer, we are basically converting every token ID to a dense vector, and this dense vector is called the embedding. So you can see here, let's say xi is your token. So we are computing the x token for xi, embedding for the xi, which is ei, and ei lies in d-dimensional space. When you are writing r to the power d, this basically means that this vector, this value ei lies in d dimension. That means it is represented using d-dimensional vector. Okay. So in reality, when we are using these models, the d could be like 768 or 1024 or 4096. Right? So like when for any given generating the embedding, it could lie in 768 dimensional space or 1024 dimensional space or 4096 dimensional space, and so on. So after generating the token, we are processing the tokens and then generating the embedding out of the token. And embedding, what is embedding for any word? It's a d-dimensional vector representation of the word. Okay. Now this might be coming in your mind that how do we generate these embedding? Okay. So that we are not covering in this session, but you can assume that there is a process, there's a let's say model in which you give your word, give your token ID, and it is capable of generating the embedding. So so everything this is going to be based on the training. So your model has been trained, and then because of the training, it has got this capability of converting tokens to the embedding. So we are assuming here that model is available, or that layer is there, which is capable of doing that. So how exactly this is done, that is not under the scope of our discussion here right now, but you need to remember this, that you are using a model here which is capable of converting your token IDs to a d-dimensional vector. Okay, and these d-dimensional vectors are unique. So if machine is having this particular d-dimensional vector that I've written here, then no other word will have this vector. Okay. So you can see, if let's say you generate the embedding matrix, then in that embedding matrix you are going to have one row in the matrix completely dedicated for one token. So I can say you have embedding matrix capital E, where you have which lies in R with dimension mod of V into D. So what is mod of D? V stands for the vocabulary, and mod of V is the size of the vocabulary, and D is the dimension. So let's say, so in your embedding matrix E, how many rows you have? You have total, it's a V class D matrix, then with mod of V rows. So one first row, second row, third row, fourth row, fifth row, like that. And then every row is of dimension D. So you have here mod of V values, rows, and then every row is of D dimension, because every word is represented in terms of d-dimensional embedding. So here you have some examples. These are just notional examples, because we say in reality, when you are converting these words to embedding, then the dimension is like what you see here, 768 or 1024. Like it's a high dimensional vector. Here we are just, for example purpose, we are using a small dimensional vector, like 4-dimensional vector here. So you see the example where machine learning is powerful. All these words are first converted to token IDs, and then these token IDs are converted to embeddings. Okay, so you can see here, all these token IDs are converted to 4-dimensional embeddings. Okay, so now given the sentence in our task of generating the next word, we have identified the tokens in the sentence. Then every token has been given an ID, and then every ID has been converted to a d-dimensional vector like this. And now whole processing is going to be done with the help of these d-dimensional vectors. These d-dimensional vectors are now going to be used for further processing. So like your machine learning is powerful, this whole sentence you can say is represented using these 4 d-dimensional vectors. Now to predict the next word, you are going to use these embeddings, and then based on that only you are going to convert the next word. So in the process, when you are processing your sentence and I mean considering the words, the position of the words also plays an important role. So like say if something is coming at the beginning, it has a different meaning. If it is coming in the between, it has a very different meaning. For example, if is coming at the very beginning, you know that it's like question we are asking, right? If it is coming in between, it has a different role. So position, when you look at a word, it's important to associate positional information also with it. So in the next phase, when we get the embedding, in the next step, we actually associate the positional information with these embeddings. So you can see here we are computing e prime from ei, right? We are computing this e prime from ei, and how do we get this e prime? We are getting e prime by adding positional information to the original embedding. So for your token, let's say xi was your token. So for xi, you have its embedding is ei, and let's say it has, depending upon its position, it has positional embedding pi. So you are adding that pi to ei to get the positional embedding of sorry, I mean the updated embedding of xi incorporating the positional information. Okay, and it is important to note down that this positional embedding is related to position, but it does not explicitly say this position is 3, right? So I mean, like when you look at the embedding, you will not directly know that this is referring to the position 3, though the value that you are seeing in that embedding will be unique for that position. And as you see from this equation, if your ei is of d dimensions, then it's obvious to say that pi is also going to be a d-dimensional vector. So if ei is a d-dimensional vector and you are adding pi to it, then pi should be also a d-dimensional vector. So pi is a vector which is, I mean, indirectly telling you the position 3 or position 4 or whatever position it is representing. So when you are adding your, your positional information with the embedding, what exactly it does? So this process shifts the token vector in a unique position dependent way so that transformer can infer order through attention. Okay? So with the help of pi, we are saying that with the help of this positional by incorporating the positional embedding information with the token, we are going to shift the token to a unique position so that transformer can identify that what that particular word or what is the position of the word in the sentence. So let's see one example here. So in the first table, what you see is the token embeddings for different words. Like machine learning is powerful. For all of them, we have 4-dimensional embedding here. For all of them, 4-dimensional embedding. Like every word is now, or every token is represented using 4-dimensional vector. Now, in the second table, we have the positional embedding. So like we have position 1, position 2, position 3, and position 4. For every position, we have got its representation in terms of d-dimensional vectors. Okay, like for every token ID, we are projecting, we are getting the d-dimensional vector. So same way, you can say that there is a model which takes the position and then converts that position to a d-dimensional vector. So we get the positional embedding here. Now, when we add positional embedding to the token embedding, then we get the final embedding. So here you can see the first value that you see is coming from the this first value is coming from the this value is coming from the token embedding, and second these green values are coming from the positional embedding, and when you are adding these vectors, then you are getting the final embedding. Okay. And in the process now, in the next, we are going to use these positional embeddings. Sorry, these final embeddings. Okay. So what exactly we mean by these positions when we are using them in the transformer? So transformer, does not see sequence order, right? Everything is going to be treated as the set of vectors. So all your embeddings that we are seeing here, or the representation of the tokens that we see, there is all in terms of the vector. So position is actually encoded in these tokens by modifying each token vector differently depending upon the index. So you can say every token is modified in position dependent way. Okay? And that is how for every word its representation gets changed depending upon where it lies. So as I was giving you the example that if you're saying I am going, and you're saying am I going, so in both these cases am is appearing, but in one case am is appearing at the beginning, in another case am is appearing as second word. And whenever you are putting the auxiliary verb at the beginning, what is the meaning? Okay, so this way, by adding the positional information with the token with the word, you can differentiate between these two appearances, and that is what exactly we are doing here with the help of positional embeddings. So here we have one example where we see there are those two sentences: I am going and he is going to the market. And let's talk about encoding going. So when you are breaking this sentence into tokens, let's say going comes out as token. So going is one token here. Going is another. Going is token here as well. Okay. So token ID is dependent on token. So whether going is appearing in I am going, or going is appearing in he is going to the market, in both the cases, token ID is going to be same. Okay. In a very simple sentence, token ID you can just refer as the index of the word in the dictionary. Right? In your dictionary, the words are arranged in an order. So we can just say that the sequence number of that, let's say the first word is given as number 1, then second word is 2 and 3 and so on. So then whatever sequence number a word has in the dictionary, let's say that becomes a token ID. Okay. So going, you are picking going from the dictionary. So if in the dictionary going is at 42 number, so then here also the 42 will come as token ID here. So 42 will come as token ID. Now for token ID, we are getting the embedding. So embedding is just dependent on the word. Okay. So I am going, here word is just going, token is just going. Here also token is just going, and for that the token ID is 42. So with respect to a token ID, your embedding is going to be same. So 42 gets the same embedding here, 0.6 comma 0.2. Here also it gives same embedding, 0.6 comma 0.2. That means we are considering two-dimensional vector representation of the embedding. In previous examples, we said four-dimensional embedding. Like here, we are considering four-dimensional embeddings for the tokens and positions. Now here, just for the simplicity, we are considering two-dimensional embeddings. So here, 42 is represented as 0.6, 0.2, and here also 42 is represented as 0.6 and 0.2. Now let's talk about the position. So position here is 3 for going position 3 is here also for going. So for position, let's say you have the I mean, for position 3, the embedding is 0.1 and 0. So this position 3 is encoded in same way. This position 3 is also encoded in same way. So when you add embedding plus positional information to get the final embedding, you are getting zero point 0.7 and 0.2 and 0.7 and 0.2 here. So until this point, you see that when you are processing these two sentences, I am going and he is going to the market. In until this point, this word going has identical representation, right? Though you can see, I mean, like the 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 meaning is very different. Like here, you are very clearly saying that you are going to the market. So here going is saying that going is telling that the person is going to market, but here that's not clear. So though this going and this going has I mean like different meaning in the sentence, but they both get the identical representation in this until this point in this representation. Now in case of in transformer, you know that I'm just mentioning that this going is in different context, this going is in different context. So in case of transformer, we see that we are using the attention, right? That, as I mentioned earlier, that the attention is like the very unique feature that we have in transformer, and with the help of that, we are able to do so much, so many things in LLM. So here, with the help of attention, we'll see that the transformer will modify these words, and we'll see that once you add the attention to these words, their representation will be different. For example, as a final embedding, if you see after incorporating the attention here, we are getting final embedding as 1.2 here and zero point 0.4 here. So sorry, 1.2 and 0.1 here, and 0.4 and 1.0 here. So word is same going here also going, but depending upon the value of the attention, you see that here the value is coming different, and here the value is coming different. Right? Different vectors we are getting for the same word, and that is possible only because of the use of the attention. So for example, here I was mentioning when we are computing the attention, in case of attention, we see for every word in the sentence, what are the other words present there, and how are they associated with the with this word that you are currently considering. So like here, going is considered in the context of I and am. Here, going is considered in the context of he, is, to, market, right? So you see, they're very clear. Clear some destination is present here, like market, and because of that, going has a very different impactful representation compared to the going that you have here. Okay. So with the help of context, we'll see with the help of attention. In case of transformer, we will be able to get very unique representation for the words, and we'll see that that will help us in enriching the representation of the word, and then also identifying in many ambiguous scenario what is the exact meaning this particular word is conveying. Okay, so this transformer block, this attention that we are talking about is coming out of the transformer block, which is like the main crux of, you can say, crux of the LLM. So this is what we can say transformers block is the fundamental computational unit of large language models, and each block here refines token representation by mixing contextual information and transforming the features. Okay, so here with the help of attention, we are going to update, we are going to transform the representation of any word, and in this process we are going to mix the contextual information. Okay? In modern LLMs, we see that we do not have just one transformer block. You may have multiple transformer blocks. So we get the representation of a word in different ways. Right? We'll see some examples, and then based on that we do the to the processing. So it's not just one, we compute the mixing of contextual information in one way. There are different perspective in which we can look at the word and then update its meaning. So in modern LLM, we see that we have multiple such blocks, multiple transformer blocks to compute compute attention for a particular word with respect to the other words that are there in the list. So mainly we'll see that the transformer block answers actually two questions for every word. First is like why, who should I pay attention to? So for every word, we are going to actually see what other words are important for it. Like when you're saying who should I pay attention to, so then in your sentence you have, let's say I am going to market. Okay, so four or five words are there. One by one you are going to process these words. So whenever you are processing a particular word, a particular token, you are going to see what are the other words which are important to this word. Okay, and based on that you'll see that you will be able to update the meaning of the meaning of these words. So one is the self attention, where we are saying we are asking this question like for every word who should I pay attention to, and second, how should I update my meaning. So once you find out that let's say for market or for going, market is important. Okay, so then how can you improve the representation of going so that now it differs from the going in, let's say, in other sentences. So once we are going to find out how important other words are to a particular word, and then based on that you are going to update its meaning. So these are the two questions or two answers, maybe you can say, we get through the transformer. So with the help of this attention mechanism, we'll see that we will be able to solve long range dependencies. As we discussed in case of RNN and LSTM, we had limited capability of remembering the memory, but here with the help of transformer, we'll see that we'll be able to remember long range dependencies, and to compute the to get the clear meaning of any sentence, uh, you need to know what was there at the beginning. Okay, so let's say you're talking about a movie, and so you at the very beginning you said that I went to watch this movie, and then you did this, and then you said you had a very bad experience. So you can say maybe so this bad experience is about the movie, but let's say your model is not able to remember that long past, then you will not be able to completely infer what has given you the bad experience. Okay, so long range dependencies are very important, and in case of transformer, we will see that we will be able to do this very efficiently. Yeah, so there are a few things that we need to know. So for example, in case of transformer blocks, it processes all the words at once. So all these words are actually whatever the word you are going to considering, let's say for predicting the next word, all these words are going to be processed in parallel, and it is going to compute self attention to relate any word to other words, and we'll see that here it is faster and efficient to handle the long range dependencies, and this feature is just coming due to the attention. So the networks like RNN and LSTMs, in case of transformer, you can say what we were doing with the help of RNN or LSTM, now we are doing in the transformer with the help of attention. So transformer actually replaces RNN or LSTM with attention. Earlier we were using RNN and LSTM to remember the memory and then predict the next thing. Now that we are going to do with the help of attention, and here we are going to have the parallel processing and self attention that as I mentioned at the beginning. So let's talk about the self attention a little bit here. So self attention actually helps a model focus on important words in a sentence while processing each word. So like you see the example here, we are saying the movie was not good. So when you are processing this, let us say you do not have good way to associate one word with the other. You are processing everything individually. Then you can see good will have a very different meaning. Good is like good is used in a positive sense, but when you are associating good to not, then you say that it is giving you the negative meaning. So for good, it is very important for it to pay attention on not, because with the help of not, you see that the meaning of the good gets updated, gets changed drastically. Okay? So to understand that uh, this movie was bad, you have to associate good to not. Alone, if you're just referring good and then trying to find out its meaning, you will not be able to do that. So when you are inferring the meaning of good, to infer it correctly, the model has to also look at not. Okay, and this we do by with the help of self attention. So when we say you pick a word and then you check with respect to that word what other words are important to it. So that's where you'll find that when you're picking good and then computing if not is important for it or not, was important for it or not, you'll see that not will have a very good, very high importance for good, because it is changing its meaning drastically. Right? So in the self attention, that's what we are saying. That the model focuses on important words in the sentence and finds out for a particular word which what other words are important. So why this self-attention comparison is useful? So, this captures relationship between the words, whether they are near and far. So now you can see for any, let's say your sentences of having 20 words. So for every word, you are going to look at all the other words that are there in the sentence. So whether you have 20 words or 200 words, you are going to compute this self-attention for a word with respect to all the other words. So here it does not matter whether it's a near or far, it is going to be computed. The relationship or the attention is going to be computed with respect to every word. And that is why it is able to handle long range dependencies. And also it works in parallel, and that is why it is faster as compared to RNN and LSTM. And it improves understanding of context. Right? Up to some extent, we were, like handling the context in RNN or LSTM also, but there it was very limited. But here, with the help of attention, we are able to understand the context in a very, very strong way. So you can see here one example that and this with the help of this you can understand what is the importance of self-attention, right? Or what is the importance of considering other words with respect to a particular word. So let's say here you are saying, I went to bank to deposit money. Now here, if you just look at the bank has ambiguous meaning. Right? Bank could refer to a financial bank, or bank could refer to river bank. Right? So whether you went to river bank or you went to financial bank, how do you know this? This can be, difference can be created when you look at other words. So for example, with respect to bank, when you look at deposit, you look at money, you find that these bank has a good relationship or strong association with deposit and money when this bank refers to financial bank. Okay, so with the help of self-attention, let's say when you are inferring the meaning, the bank looks at deposit, the word bank with respect to bank word, we are looking at money, deposit, all these words, and then with the help of that, we clearly understand that this bank refers to the financial bank, because with respect to bank, when you associate deposit and money, you find that when it happens in case of financial bank. Okay, so similarly, another example, let's say the movie was not good. As earlier also we saw the example. So if you want to negate this, if you want to find out that the movie was not good, then good has to be associated with the not. So when good attends to not, then correct negative meaning comes out. So when processing bank, self-attention assigns higher importance, that means the weight, higher weight to relevant words like deposit and money, and lower importance or lower weight to those words which are not that relevant. So for example, in the sentence you have many other words, like you have went to, etc. Like if you see I went to the bank to deposit money. So along with the bank, you have I also, went also, the also, deposit money. So in the self-attention, you will see that higher importance will be set to deposit and money compared to the other words. So what exactly happens internally when you are, processing this? So bank basically compares, like when you are computing the self attention, what exactly happens? You pick the bank and you compare that uh, to all the other words that are there in the in the sentence, and then find strong similarity with the finance related words, and that gives them higher attention score. Okay, and please remember, when you are saying you are comparing bank with the all other words, it is not just that you are doing it with bank only. You are doing this for every word that exists in the sentence. So you are going to compute attention for every word. You are going to compute attention for I also, attention for we went also. You will not have clear meaning of bank, but with the help of this contextual information, when you associate attention to bank, then the meaning of the bank is becomes very clear, right? So that means if you, let's say, see two sentences, in one sentence you are saying I went to bank to deposit money, or in another sentence you say I went to river bank and enjoy it. So in both the cases you'll see that this bank will have a very different representation, very different embedding, final embedding that you will get after attention. But otherwise, if you see only the let's say token embedding and then maybe positional embedding, you may have very similar representation for the bank. But when you are associating the attention, then the meaning becomes very clear. So what is the result of associating the computing the self attention for a particular word? So meaning becomes very clear for every word. I mean, it's not only with respect to the bank. For every word, the meaning becomes very clear. So bank here, after computing its association attention with respect to the other words, you find that here we are talking about the financial institution, not the river bank. So we just said that bank compares itself with all other words and finds a strong similarity with finance related words, right? So the question might be coming like, how does it find high similarity with the finance related word? So we see what self attention does. It actually asks a simple question. This we saw earlier also, like which words in this sentence help me understand bank? Again, you read it, what self-attention does. Self-attention asks this simple question: which word in this sentence help me understand bank? So our objective is to understand each and every word in the sentence. So self-attention helps us in asking this question and then getting the answer, that which word in this sentence is going to help us in understanding a particular word. So let's say you're talking about the word bank, then with the help of self-attention we'll find out whether this particular word, let's say deposit, money, these are the words that are going to help us in understanding the meaning of the bank. So step by step analysis. So bank looks at the word, let's say I, which it finds under not relevant, went also not relevant, but deposit and money, they are relevant. Now again, the question, if you this question may be in your mind, that how does we know bank is relevant to deposit and money, not with the let's say I and when and so on. So here again the learning comes, learning plays a role. So it has been learned from the training data. So like words like deposit, money, loan, these are usually referring to the financial banks. Okay, river, water, they are usually referring to the river bank. So so based on that, it gives more importance to familiar related words. So the bank here focuses on deposit and money, and then based on that, it is understood that we are referring to financial bank. So let's understand this transformer in a little more elaborate way, where we are going to discuss different phases that we have in its implementation. So first we already discussed that we are going to compute the token, and then we are going to associate a positional embedding with the token, and that's how we are going to get position associated embedding for every token. So let's say here this V vector is representing that. V vector is representing the token. For every token, the token, its representation after incorporating the position. Okay. Now the role of the transformer comes. So we have said that attention, where are we computing the attention? Attention is coming after computing the embedding of the token and associating the position. After adding the positional embedding to the token embedding, then whatever we get on that, we do the updation based on the attention. So to compute the attention, here we are going to, with respect to every token, we are going to create, you can say, these three uh, three things. One is queue, which is called query. Second is key, k, which is called key, and third is the value. Okay. So for every token, we are going to do this, right? Please remember, with respect to every token, we are going to get Q, K, and V. So for example, let's say X is our token. Okay. Like here we are trying to understand bank. So let's say bank is the token. Under consideration, the bank is there. So with respect to bank, we are going to get these three values, Q, K, and V. And same way, all the words that we have in our sentence, for every word or for every token, we are going to get these three. We are going to create these three things: query, K, and value. Right? These are also going to be in the form of a vector. We see. So each token vector is going to be linearly projected with respect to these matrices WQ, WK, and WV, and then based on that we will be getting Q, K, and V. Now, what actually exactly we get when we are projecting our original embedding to these matrices? So we basically intuitively we can understand. So what we get through Q. So Q actually tells what this token is looking for. It tells what this token is looking for. Like for example, bank is looking for money, bank is looking for deposit. So Q tells us what this token is looking for, and K tells what this token represents. Okay, what is the representation we get out of that token, and V is information carried forward. Right? So for every token, we are computing these three things, QKV, and QKV are computed with the help of these matrices WQ, WK, and WV, which are, you can say, they are learned. They are during the training. They are learned. WQ, WK, WV, they have been learned during the training, and based on that, those values we are actually generating the QKV values here. So again, we're not talking about how do we get WQ, WK, and WV, but you can say, let's say for a transformer, these values during the training we have learned them, and then now we are just using them. Okay. So after this, I hope the process is clear. For every sentence, you have, let's say, n tokens. For every token, now you have computed its Q, K, and V value for it. And then now we are going to compute the attention, right? So next thing is to compute the attention. So how are we computing the attention score? So to compute the attention score, we are associating Q with K. Q is for the ith token and K is for the jth token. And this score ij that we are going to get here is basically the attention score that we get for associating query Q to key K. Query Q is with respect to ith sentence, ith token, and K is with respect to jth uh, jth token in your sentence. So like for example, you can say your query is going to be bank. Query is going to be bank. Yeah, query is bank, and let's say, sorry. Yeah, query is bank, and then you are associating bank with, let's say deposit, right? So deposit is your, so as I said, for every word you are computing, it's Q, K, and V. Here for this also you will be computing Q, K, and V. Now you want to find out the attention score when you are associating bank with deposit. Okay? So that is what we are saying. We are associating Q of this. Let's say this is ith token and this is jth token. So you are associating Q of ith token with the K of jth token, and that way you compute the score ij, which is the raw attention score for ith token. Okay, so this is basically telling us how relevant is jth token j to token I. Here, the same thing we are computing. How important is this deposit to bank? That is what we are getting here as a attention score. High the score, more the relevance. For example, you find that with, when you are associating bank with the deposit, you get a value, let's say 8. When you are associating bank with, let's say, going, you are getting score as, let's say, 5. So then you can say, depending on the score, you can compare and then find out which one is, which association is more important. So here you see example, that when you are associating I with am, or I with going, I am with I am with am with going, and all that. So some values you see here. These values are nothing but the score values that you get when you are associating a particular word with the other word, and that we sometimes refer as this matrix QK transpose matrix, which is nothing but just this matrix, that this data that you see here, 101, 011, 112. So QKT, this matrix we get when we are computing the association of words with other words. Okay, so I hope everybody is now clear. How are we going to compute the attention score for the words or the tokens that you have in your sentence? So what computation that we are seeing here with respect to ith token and its association with the jth token. Now this you can extend your I from 1 to n, j from 1 to n, and then you can compute all these, all the associations, all the attention scores or attention score for every word that you have in your sentence, and that is what in short being shown here in the matrix. So like I am going, this is a simple sentence. So you want to find out when you are associating I with am, I with going, what is the score you get, right? That is being represented here. So your whether sentence is small or big, for your sentence, you are going to uh, consider every token one by one, and then you are going to associate it with all the other tokens in the sentence, and then going to compute this score, which is going to be called as attention score. And this score basically tells us how important a particular, how relevant the token j is with respect to token I. Now I and j, you can see they can range from 1 to n. So with respect to ith token, you can find out the importance of jth token, and then that you can represent here as attention score. And then we'll see later with the help of these scores only, the representation of the words will be updated, because after the attention you have to do something so that the meaning of the bank, let's say right now we are talking about representing bank in such a way that it clearly tells us that this bank is referring to financial bank. Okay, so with the help of this score, we'll see, we will be able to update the meaning of the representation of the bank or the embedding of the bank. Now, when we are computing these scores, you know that you are doing like a dot product between the vectors. This score computation is like, you see here q k transpose. You are basically multiplying the q to transpose of k. Right, transpose you are just taking so that you can take the product. So this is basically dot product you are computing between the two vectors. And if the size of the vector becomes more, you know that the value will be going out of proportion. So then you need to have some way of managing these values, right? Maintaining the scale, like bringing the values in within the scale. And that is why we are using a very simple way of scaling down the values, where we are dividing dividing all the values of the vector by root of dk, where it represents the dimension. So let's say we are talking about the two-dimensional embedding here, so we have to divide every value by 1.4. Okay, so second step. So after computing the scores, we are going to normalize the scores, and these are, this is the equation for getting the normalized score. So every QKT, every value that you have got after multiplying QK K transpose that is being divided by dk, and you get the normalized value. So it's simple. Like here, this was the original matrix here, and now every value is divided by 0 root up to, that is 1.41, and we are getting these normalized values are right values where the scale is now reduced. Okay, any questions so far? Okay, fine. So let's move forward. So after computing the score, attention score, our objective is to update the representation of the word, and that word basically that representation is computed here. You see, with the help of we have computed, or we have obtained 3 different quantities for every embedding, every token, you can say q, k, and v. So we see, with the help of q and k, we are computing the attention score, and by using that attention score and then this value v, we will be able to update the representation of the word. If, for example, bank, it's what bank basically represents in the form of embedding, that is here in V. Now this value we will be enhancing by using the attention score that we computed with the help of Q and K. So in this remaining part, we are actually going to see that. So after computing these normalized scores, or after bringing down these values to a scale, next that we are going to do is applying the causal mask. We'll see that what exactly we mean, and then softmax again for the normalization, and then after that we are going to compute the weighted sum of v, and this weighted sum of v that we are going to get after the step 1.6 is going to be the final representation of your token. Like let's say bank, we are doing this whole exercise for the bank, or maybe going here in this sentence. So then that is going to be v for going is going to be the final representation for it. Okay, so now what is this causal mask thing? Let's understand that. So when you are predicting the next token, you are saying, let's say your sentence is I am going. So when you are doing the training, you would like to only show you would like to only show to your model what you have already seen, and based on that you would like to predict what is going to come next. So during the training, you see that I is predicting I am. Okay, let's say we are talking about the prediction of the next token. So I is predicting I am. Then with the help of I am, you are predicting going. With the help of going, you are predicting the next token, let's say whatever it is coming out, maybe full stop or market or whatever. So in this process, you want that your model should not see what is going to come in future. When you are training your model, you should give, let's say, I and am, and you should ask model to predict. And let's say it predicts something, and then based on that you can compute the error, and then like retrain your model so that the error is reduces. So when you are training your model for predicting the next text or next word, your model should never see the future words. Okay? So for example, here when you are let's say computing what is going to come after I, so then I should not know that in the training data am and going is there after it. Or when you are saying I and am is going to produce going next, so then in the training data the going should not be there. Okay? So what essentially we are saying here that when you are training your model for predicting the next word, then in that case, you should not tell the model what is going to come in future, right? Model should predict the future. The model should predict the word that is going to come in future, and then based on the ground truth, or based on the like output, given output and the expected output, we can compare and then find out the error. So if the model knows what is going to come next, then it will be biased about that. And that is why, just to handle that, we are using here the masking. So what we do when we deal with these attention scores, we don't associate I with am and going. We don't associate, let's say, uh, this when we are, let's say, talking about I, we don't tell model that I am and going to come next. Or when we are talking about I and am, we don't tell the model that is going to come next, and so on. So future we do not tell. And just to avoid that, we are doing the masking. So in these scores, in this matrix, you are having association of every word with the other word. But now here we are just masking. So for those words whose association we don't want to take into account during training, we are just putting a very low value here, right? Like minus infinity. So just to show that it's a very, I mean, there's no relevance. So here, when you are processing I, you don't want to use am and going, so you just put minus infinity here. Similarly, when you are processing I and am, you don't want to make use of going, so you are putting minus infinity here, and so on. So when you are, let's say, processing I am going, then all these three things are important, because you are, after that you are going to predict something. So we are going to put minus infinity here, so that this masking is going to be done, so that uh, we mask all the future positions, right? So at all these future positions we are putting minus infinity. So what are the allowed positions where we are not going to put minus infinity? These are all positions, all these tokens up to the current one. So for example, current one is your let's say am. So up till that point you are using non-zero, and then up till that you are using minus infinity. Okay, so when you do actually this minus infinity, you replace by these values by minus infinity, and then apply the softmax for normalizing these values. You find wherever we have put minus infinity, after this normalization we get the value 0, right? 0 0 here. Similarly, in second case 0 here, third case no 0, right? Because there was no infinity. So, and since we are using this softmax normalization here, we find that all these total weights sum to 1. Okay, so one way we are able to normalize these weights, total sums to 1, and also we are now able to assign weights 0 to those associations which we don't want to consider during the training. So once we get this updated attention score matrix, right? These are attention scores only, but here we have just suppressed those attentions with which association we do not want to consider. Okay. So now with the help of alpha ij, with the help of these attention scores, we are going to update the meaning of our representation of the words, and that's what exactly we are going to do here. So the let's say your sentence is I am going, and here you have matrix V, which is representing these embeddings. Like I, for I, this is the representation. For I am, this is the embedding. For going, this is the V vector. Right, for every vector, for every word, you remember at the beginning we said that QKV we are computing. So they say V is for these tokens, this is the V value. And for every token, we have also computed the attention score. So now we're going to compute the updated value for the token, or for token embedding. You can say that it's a context vector we are going to compute, where we are going to associate V with the attention. So by incorporating attention and this V values for the tokens, we are going to get the updated vector for these tokens, and that association is going to be done with the help of this expression, where we are going to multiply alpha ij to vj, where j is going to range from 1 to n. So you can see here, this is your V matrix. Exactly, say this thing. These two are copied there. So this is a V matrix, this is the attention matrix. Now you're going to multiply. In this case, in this the last table here, you have weights, these weights written here, and these V values written here, and then alpha I, this product is being computed, alpha ij into Vj here. So by doing that, so it's like multiplying this first weight to first vector, second weight to second vector, third weight to third vector, and then adding them. So we get here 1, 0. Then again here, multiply this to first vector, this to second vector, this to third vector, and then sum that. So you can see here only 2 vectors we are getting here, and then summing them and getting this. Third vector is like resulting to 0. Right? In the third case here, all these 3 vectors are considered while adding up, and then we are getting the value 0.8, 0.8. So this is actually what we get at the end, final. So for I am going, whose value was 1, 0, 0, 1, 1, 1 for I am and going these words, now they get updated to this. So I has representation 1, 0. I am has representation 0.3, 0.7, and going has now representation 0.8 and 0.8. Now this representation, we say that this is this representation has I mean, these are the again you can say these are the embeddings for every word, but they are now context aware embedding, because here with the help of attention we have updated their meaning. So after this step, you'll see that you can say if you have a bank in reference to river bank and a bank with reference to financial bank, you will find that they will be very differently represented here. Okay, now so by using one attention, we have updated our embeddings. Now attention can be, so this association can be defined in many different ways. For example, it could be in terms of syntax, that let's say with I am is going to come, so there will be association with I and am. Semantics, for example, you're saying word bank is semantically more meaningful with the deposit and money and so on. Tense, long range dependencies. So relationship, like when you are associating a word with the other words and computing the attention score, this association can be thought of in many different ways. You can have many relationships to define the association, and based on that, you can say you can have one head, head to compute those attentions. So that's why we are saying here multi-head attention. So let's say you have 4 head for computing the attentions, and one is computing with respect to syntax, another is with the semantics, third with respect to tense, maybe next with respect to long range dependencies, and so on. So if you have, let's say, one attention block, then you will become able to compute one type of attention. If you have multiple attention blocks, then you will be able to capture multiple ways or multiple relationships that exist between the different tokens in your word. Okay, so what we have got until this point, we got the representation of our token in an updated manner. Now it has the contextual information. With the help of attention, we have updated its representation. We have made the updation rich, right? So we have got the embedding. Now when we are dealing with the long networks, you might have heard of the problem of residual. Problem of what do we say? The exploding gradient or vanishing gradient, like where the gradient. When in the neural network, when we are training the neural network, we are actually updating the weights, and weight updates happen based on the gradient value, right? And gradient is nothing but the derivative or the difference, you can say, and that difference vanishes or becomes very huge when we process the values through different layers, large number of layers. And just to handle that problem, the solution suggested is called the residual connection, where after getting, let's say, some updated representation, you add your original representation to it, so that your representation is not forgetting what actually it was representing. So with the help of residual connection, where you, like, context is something which you got, or you had a token, for that you got the contextual representation, and X was its original representation. You are adding X to the context, so that you are able to ensure each token remains or retains its original information, and also prevents forgetting the its own identity or own embedding. So I mean, like this happens when you face the vanishing gradient problem. So just to avoid that, we are adding skip connections, sorry, residual connections, and uh, effectively what we are doing here is that we are adding the original vector from where we started to your current embedding that you have. Okay. So this helps in stabilizing the training process, and as I said, helps in avoiding the problem of exploding and vanishing gradient. Okay. Then you have some normalization steps, like uh, you have a uh, I mean, this simple way of normalizing. If you see, this is x minus mu divided by sigma into gamma plus beta. These are the learnable parameters here, gamma and beta. Mu is the mean of the vector, sigma is the standard deviation. So you might have heard of z-score normalization. So if you just convert, let's say you remove this part, make beta 0, this make it 1, and then you'll see that this is nothing but x minus mu divided by sigma. Right? To make it more effective, we can incorporate these learnable parameters with it, and then do the better or enhanced uh, normalization. So after computing the vector, after adding the residual part to it, whatever we have got, we are just with the help of this, we are trying to normalize normalize the representation. So you can see it is in through all these processes, our whole interest is in making the representation of the token as rich as possible, as clear as possible. So let's say we started with the token original representation as this, then we got the contextual information as this, then we added the residual information, and then we got the x plus context, and now we are normalizing this representation, right? And why we do normalization? So you know that you don't want to I mean, like you don't your values to become out of a range. You always want to fix them within the range, and that is why always we go for the normalization. So I'm giving you the overview after every step, so that you understand what exactly we have got until this point. So again, to repeat what we have got until this point, we have different tokens, and for that token we have through these steps we are trying to get updated, clear information, clear representation. So in totality, for every token we have got some embedding for it. Okay, and in subsequent steps again we are going to make few more efforts to enhance the embedding. So one way to enhance the embedding or enhance the enhance the representation of a vector is like projecting your vector to a higher dimensional space, and then again bringing it down to the original space. So this is a very common technique we use to enhance the representation capability of the embeddings. So what we are doing here, that we are using this matrix W1. With the help of W1, your original embedding X is projected to a higher dimensional space. So W1 is a weight matrix, B1 is a bias matrix. Again, for this projection also you have a network with the help of which you are putting your vector, and then it is getting projected to higher dimensional space. So here let's say originally your vector is of 4096 dimensions. If you remember earlier we talked about the dimensions of the embedding. So one of the value that we mentioned there was 4096, where originally we represent our embedding. So here with the help of this linear expansion, we are projecting them to higher dimensional space, and again then we are performing some non-linear activation to add more expressive power, and then again we are bringing the representation down to original size. Okay. So you can see here earlier we were doing the linear expansion, here we are doing the linear compression. And this process, so like we started with 4096 dimensional vector, we expanded it to higher dimension, then again we brought that down to 4096. Now what we got, so through this process we see that this representation gets enhanced. For example, Right now, when I mean originally when we were using this 4096 values, the representation was not very clear. Now, after projecting it to higher dimensional space and then again bringing it down to the original space, the vector that we get is having better representation. So for enhancing the representation of the embedding, we are doing this exercise. Okay, so this is a summary of what we are doing in case of expansion and comparison that I just explained to you. Then again, we have this adding of the residual, or we have the residual connection where we are adding whatever we have got here with what original representation we had, so that we don't. I mean, after that, I mean, after every few step, we are doing this exercise so that we don't. We also, in this representation, do not forget its original, I mean, like essence. So after performing some processing, we again add the original value to this, so that in some way we are also carrying forward what exactly this particular embedding was at the beginning. Okay. Okay. So here you see that, let us say by applying this process that we have just seen, and what we have done until this point, there was a token. For that token, we have got an enhanced embedding with the help of adding the attention, then projecting it to the higher dimensional space, then bringing it down to the lower dimensional space. So now you can see that this is final output of one transformer block, right? Because one attention you are adding with respect to one transformer block. So let's say you are using multiple types of attentions, like you want to incorporate multiple types of attentions. For example, one learns the grammar, another learns the phrases or meaning, or maybe four. I mean, you want to have different attention blocks. So for that, you will be having many transformer blocks. So far from every transformer block, you will be getting an embedding. So at the end, you are basically going to concatenate all those embeddings and going to get the final embedding. So here, output of the transformer layers, if you have one layer, like one transformer block, you are going to get one embedding as an output. If you have n transformer blocks, you will be having, so let's say one embedding is of d dimensions, right? For every token, you are representing it in d dimensions. So if you have only one transformer block, then final embedding will be of d dimension. But if you are using, let's say, multiple transformer blocks, so then depending on, let's say, 3 you are using, so then final embedding is going to be of 3 into d dimensions, right? Because you are just going to concatenate all of these tokens, these embeddings. Okay. So here, let's just take a simple case where, let's say, we are considering the output of the final output of the transformer block, and you have just one transformer block. So whatever output you are going to get from a transformer block, we are calling that final output. We are calling that as hidden state. Okay, just remember this name, hidden states. What are the hidden states? Hidden states are those values which are making the final embedding vector for your token. So we are going to get one vector per token. And what is the dimension of this? You can just see, earlier we said that embedding is going to be in d dimensions. This is also in d dimensions. And final outcome of the transformer is in d dimensions. Now this could have been 3D. Let's say, if you, I mean, 3 into d, if let's say 3 transformers are used. Okay, so ultimately with the help of this, you are actually getting this capital H, which is the embedding for your token, and that you can say is context aware representation. Okay, that is the context aware representation of the token. Now we have got the output of the transformer, but what was the objective? Objective was to predict the next token. So next token, now we're going to see how we are going to project the next token given this hidden state. So for that, we will see that we are going to use a linear projection, and for that we will be using a matrix W, W vocab here, and that again, like earlier, if you see, we have used some matrices to compute Q, K, and V. Similarly here, W, this W matrix is also coming out of the training. We will just making use of that. So at the final step of the model, the transformer produces hidden state vector H for the current token, and that H is going to be belonging to the dimension of the model, and we are going to convert this hidden representation into logits for every vocabulary word, and for that we are going to use this equation. So now please remember, with respect to the token, we have got this hidden state. Now, with the help of this hidden state, we are trying to find out from the vocabulary what is the next word that is going to come. So, you know that what we finally compute, we compute the probability for it. So here, this Z that we are getting is in a sense probability with respect to every word that exists in the dictionary. So you can see here, H, the final is hidden state representation. W is for the this I mean W weight matters with respect to the vocabulary that you have. W B is the bias vector. So W and B, they are learned during the training. So I mean, how are they exactly learned? We are not discussing, but they are learned during the training. Then Z is the final logit, or you can say in a very simple term, the probabilities with respect to every word that you have in the vocabulary that you are going to get here. I just skipped this part. So W vocab is actually learned, as I said, that W vocab is a weight matrix, which is with respect to the vocabulary, and with the help of this only, you are going to perform the projection, and then going to find out the probability and the logit or the probability values for every word. So let's understand this with the help of one example. So let's say this is the matrix. This is the equation that we just discussed that we are going to use for computing the probability value for all the dictionary words that we have with respect to the hidden state HN we have for the last token. Say the hidden state for the last token is this. Now, objective is to find out with respect to this token, whatever words you have in your dictionary, for all those words with respect to this token, what is the probability of these words coming as the next word? So for that, we are going to use this. We have W matrix given as this, B matrix given as this, and H. How did we get this H? So we have discussed all these steps to process the token and then find out its context-aware rich embedding. So that is so this is the output of the transformer that we got, and then we are putting this simply this H value, W value, and B value. We are just putting it in this equation and then computing the Z. So now this Z is going to be computed with respect to all the tokens. So what is this token 1, 2, 3, and 4? These are the basically you can say tokens which are probable, which are possible, which can possibly come as or next token, or you can say they are part of the dictionary. So here the logit value is coming as 0.4, 0.74, minus 0.28, 0. And with respect to this equation, these are the values of Z. Right? W is known, B is known, and HN also we have got. So with respect to that last token, last embedding HN, we are computing the logic values for the possible words. So here, so in this example, you can say what is going to be the most probable word to come next? To T1. Okay. Now, what is T1? Like here, we are just using a notional names like T1, T2, T3, T4. But in this example, let's say your tokens are I am going to market. Okay, and our objective is to predict the next. So what is the last token here? Last word is market. So with respect to that, we will be, let's say, getting the embedding H market, and that H market is this. That means this is the, with respect to market, this is the final embedding coming out of the transformer. So with respect to that, let's say we are computing the Z, and in your dictionary, let's say these words are there. full stop is there, home is there, now is there, today is there, right? These are the tokens from the dictionary. For every dictionary word, you are predicting what is the probability that it can come as the next. So H market is the embedding for the market. W is the weight matrix for the with respect to your vocabulary that you are having, and B is the bias vector. H and W and B, as I told, they are learned from during the training. So with the help of this, we are getting with respect to market Z, and here we see that Z with respect to full stop is 0.74. Right? So what this finally says. So now, I mean, this logic scores can be by using the softmax normalization. They can be converted to the probability. So for example, these values, you are applying the softmax on that, and then they're getting the values between 0 and 1. These are, you cannot directly call these values as probabilities because there are some of them negative. You can, you know, the probability cannot be negative. So by using the softmax normalization, we are converting them to probability, and now we find that dot has the highest probability, full stop has the highest probability, and then this basically says that the next token that is going to come after the market is full stop. All right. So I'm just maybe taking 1 or 2 more minutes to conclude. So until this point, we have seen that given the token, given a sentence, and then by knowing what is the last word there, and then getting its updated contextual representation, we can predict with the help of the transformer, with the help of attention, what the word is going to come next, right? And this we have seen here with the help of this example. So this last thing, what makes the LLM very large? So you know that we have billions of parameters here, a lot of things to do, and for that, obviously, you will have a big networks and a lot of connections there, and then because of that, you will have billions of parameters. And to train such a huge thing, you also require massive training data sets. Like when your network is large in the proportional way, you also need a large data set to train it. So massive training data set is required, and then also pre-training and fine-tuning is required when we are using LLM. Like if you, let's say, use some foundational model and then you want to customize it for your own purpose, then you can also perform the fine-tuning. Okay. And there's a lot of possibilities, a lot of capabilities these models have, and we can develop many different applications like chatbot and assistant, code generation, search summarization. We can customize these LLMs for our specific task, for example, healthcare, education, research, by using the pre-trained model and then retraining them. So there's a lot of potential in the LLM. So with this, I just conclude myself here. I hope you enjoyed the session. If you have any question, it will be really nice to get them and discuss.
Thank you so much, sir, for imparting such an invaluable information to us. All the participants are requested if they have any question, please unmute their mic and ask it. Sir, I think there is no more questions from participant side.
Okay.
So moving toward the conclusion of this session, I would like to invite Ms. Neha Sankwar, ma'am, for vote of thanks.
Good afternoon, everyone. Thank you, Sejal. Thank you, sir, for delivering such an informative session. You explained the concept of large language model in a simple and understandable manner. The way you connected theory with examples helped us to gain a better understanding and made the session engaging and easy to follow. Your valuable insights will certainly support us in our teaching and research work. So, lastly, thank you so much, sir. Thank you all the participants for their active participation. So, with this, we conclude the second session of day 4. Thank you, everyone.
Thank you. It was a pleasure.
Sir, one question.
Yes, please go ahead.
The question is from Nandyam Yadav, sir.
Mhm.
What is the accuracy percentage for different language model and which one is the best on performance basis?
Yeah, so the accuracy, I mean, you can see their documentation model. So accuracy depends on like what, in what in what context you are looking at them. I mean, different models have different capabilities depending upon in what context you are using them. I mean, in a as a end user, I think most of these models are like very well trained, very efficient model for us. But to find out exactly how much accuracy they have, I think for if you just go through the documentation of these models, you'll find out in different scenarios what accuracy they got. So for that, I would recommend all of you to check the documentation of these models. Right, you will get the details there, like GPT. And there's so many models there: GPT, Llama. I mean, like lots of models, and in many different scenarios, they are claiming their accuracies. So, I mean, I don't have that exact value here. And as far as I mean, they are concerned, let's say if you're talking in terms of applying them for our own use, then it quite depends on how you are going to retrain them. So that's where the customization comes in, where you consider the pre-trained model and then train them. So how efficiently you are able to train them, that is going to determine how efficiently you're going to use them for your own purpose.
Thank you, sir, for patiently handling the questions. Thank you so much.
Okay, any other question anyone has?
Is there any question? Please unmute your mic. Sir, I think there is no more question left.
Okay, no problem. So yeah, so I think we can conclude the session. Thank you, everyone. It was a pleasure delivering this session. Thank you. Have a nice day.
Thank you so much, sir. You too.